everyone. Thanks for coming to today's session. This is Xin from Microsoft. I have Wei from Nvidia. He's a principal software research architect with me. We also have Yan Zhao jointly create these slides, but he's sitting in Seattle, cannot join us. We are here to present the SONiC community only, not Microsoft or Nvidia specific solutions.
Yeah, so don't ask me a question like, Ethernet or InfiniBand, which one is better? So I will not answer this question in the next 30 minutes.
Okay. With that, let's take a look. So while we are all enjoying the excitement of the AI bring to us, a lot of innovations, inspirations, and also a lot of opportunities. Behind these opportunities, actually this is a public data, right, are how large the data set is, how they are connected, and how that the model is growing to support the end user like you. Behind it, it will be us. Behind it, there are multiple big challenges about the hardware to support on one unit, like a GPU, like all other AI silicon, to support computation, to support the more and more fast, powerful, like single unit computation. Second is the computation unit become very, very powerful and also very, very power hungry. They need to drain a lot of power, right, to support large pool of data. Last but not least, we think it's a fundamental issue. It's actually belong to networking, where we have to transfer a lot of data in the pool to let them to connect to each other, to reference, to index, to find, to search, to train, so that they can form a solution, form some answers to feed to the customer. So among all these small numbers, small found digits, right, there are many, many zeros behind it. Those are the size of the data. Need to be used to build solutions, build answers for everyone who use it, and also for us to connect them, to transmit them, to send to each other using very big bandwidth, very small latency, to jointly deliver a job. So there's a lot of job security here, but I see that is a lot of excitement for the networking community. While the data set is growing, right, about the net, this is a typical topology to connect the user to the cloud, and behind that cloud, connect GPUs or other AI end unit to each other. The front end connect to the internet, VMs or bare metal, allow access to the cloud and allow access between compute to storage. At the back end, there is a giant network now become more and more demanding, more and more high bandwidth to connect all the computation unit together as a giant pool to perform the computation needed by AI or by machine learning. Two places are evolving, right? One is within a server, within a rack, that all the GPUs or AI endpoint need to connect together and to perform the computation. That we call it scale up. Scale up is still not enough. We have to connect even more large scale of a large number of the endpoint unit, GPU or AIS silicon together. We call it scale out to perform a large scale pool of data transmission, data exchange, training, inferencing to provide the satisfactory answers to the customer for their like video, text, all the intelligent work. How about on the hardware side? We see hardware side are matching, are evolving very fast to support this trend. We have using example on the GPU when they evolve from V100 to GB200. You can see that on the NVLink side, it evolved from 300 Gbps to 1800 to support the scale up connectivities between GPU within a short distance, connect to each other for jobs. Well, we use NIC to connect in the backend network, scale out, also to form a bigger pool, to do large model, to form a large scale pool for the more computation tasks. With that, we take a look on the hardware side. We are evolving very fast. This is just today, right? Tomorrow it will change. Like in a few months, in a few years, we see that this change and this evolution is doing acceleration. It will not stop. Then let's take a look on the traffic side, on the application side. What's the characteristic of AI workload?
Yeah.
Wait.
So yeah, in these slides, we give two representative collective operation. Right, the first one is O reduce, the second one is O gather, because this kind of collective operation, they are the main source to generate traffic in the AI workload. So a lot of people talk about collective communication. Okay, let's take a look of the O reduce. In the O reduce, right here we have 4 GPU. All the 4 GPUs, they have some data in the input buffer. So we want to perform a reduction operation by taking all the input data. So a reduction operation can be like a sum, can be a min, and can be a max. So here I use the sum example. So we get a sum of all the input data from all the GPU. Okay, so we get some result, which is the out. And we want to ensure that all the output buffer of all the GPU, they have this out result. So as the name suggests, right, O reduce means that I perform reduction operation on all the input data, and I want to ensure that all the GPU, they have the result. So of course, right, the collective communication is very important in the AI workload, right? We want to achieve high performance communication. That means we cannot implement them in a very straightforward way, right? We need to use beautiful algorithm to achieve high bandwidth efficiency. So in today's collective operation, I mainly implement using the ring algorithm or tree algorithm. Okay. So given the collective operation and such kind of algorithm, right, what are the interesting observations? The first observation is that in the AI workload, right, in the collective communication, there are not so many flows. The key reason is that if we go back to the tree or ring algorithm, right, one GPU node only talk to a few other GPU nodes. It's not like anyone talk to anyone. So there are not so many flows in the network, and we call this low entropy. The second characteristic is that the tail latency has a big impact on the completion time of the collective operation and also job. And that is because a collective operation will generate a lot of flows. And the collective operation can only be complete if the last flow has been complete. So in this example, right here, even though most of flows can finish maybe in several hundred, but actually the collective operation completion time depends on the slowest flow, which is 5,000. Okay. So after we talk about collective communication, traffic characteristics, okay, let's go to the cloud. Okay. In the traditional cloud, right, we have the multi-tenancy issue, and on every physical server, right, we run multiple VM, which can belong to multiple tenants. Okay, so they compete for the memory or CPU, right? There are a lot of a noisy neighbor problem due to the host resource contention. But in the AI cloud, right, the customer, they commonly run dedicated GPU server, so nobody want to share DGI server with another guy, right? So in this case, there's no resource contention at the end host. But the network fabric will become the primary cause of the interference in the AI cloud. So given this, what are the uniqueness of the AI networking? So I borrowed the slides from Jeff in his presentation in the SONiC AI working group. So compared to the general purpose cloud network, the AI cloud network is designed for tightly coupled performance-driven distributed application, that is machine learning. And we need to achieve high effective RDMA bandwidth in this network. It has low jitter tolerance because the job depends on the slowest flow, and the switch and link failure has a big impact on the AI workload. Because if you have a switch or link failures, your RDMA connection may be terminated. If your RDMA connection is terminated, your NICO will report error. Once your NICO report error, your job fails, and you need to relaunch the job. Okay, relaunch a job for the big model, training is very expensive. And last but not least, the AI cloud network is designed for high performance at large scale, at a high load. So in such kind of like performance-driven network, right, the hardware can provide high bandwidth. But how to utilize the high bandwidth provided by the hardware? The TCP/IP is no longer enough, and so we need RDMA. So the figure on the left shows a traditional RDMA where the NIC can help, can exchange the data between the memory of the two hosts. And we know that in the AI, right, the GPU, rather than CPU, right, the GPU is the first class of citizen. So we need GPU direct RDMA to exchange the data between DRAM of two GPUs. So, but no matter traditional RDMA or GPU direct RDMA, they both require the support of the switch to achieve high performance.
Yeah. Thanks, Wei. So hopefully that Wei just talked about that in order for this high performance, low latency data transmission, RDMA is a must. I'm going to talk about what's inside SONiC now. This is good news, right? As one foundation is already done for you. So SONiC has RDMA enabled by day one. They have basic functionalities like profiling all the QoS parameters, support ECN traffic, PFC for the flow control, and buffer allocation, tune the buffer allocation, as well as that telemetries, right, to understand how it performs. It doesn't stop here. It also went far to advance RDMA, right, to support if your architecture has single tour or dual tour, it has specific handle. If it has dual tour, might have the bounce back routing problem. It is taken care of. It also adds a lot of telemetry, like Q watermark to understand the dynamic of changes, string telemetry to send them out. It's one thing to config, make it work in the whole network, right? It's a whole art to also continuously keep it perform at the desired bandwidth or QoS performance. If there's anything happens, right, for the AI, the computation is so high, like any failures will have a big impact, we should quickly detect it. So you can see that we configure it right, we have the mechanism configure it right. We also have the mechanism to detect and always monitor, watching it if it's continue to perform well. Or also have this, the test case. Test suite really simulation and to test this very fine-tuned or configured parameter if that is working fine. So we have looked at the system. AI has a very giant data transmission, bring a lot of challenges to the network side. The hardware side is evolving fast. Generation after generation, the speed is doubling, tripling. We look at the data traffic characteristic and what we need to support, right? We share the source that RDMA is needed. The good news is foundation is there. But looking forward, there are multiple other sources. RDMA is not enough. Here, we are going to share what else we think it will come to support the AI networking for AI era.
Yeah. So while RDMA can ensure the high-speed transmission between two nodes, right? But in the AI, right, we have so many like GPU getting involved. So that means we need to ensure that all the nodes, they can transfer data at a high rate. So this essentially is a load balancing problem in the network. And today's practice is equal cost multipath, ECMPs. Okay. So, but unfortunately, ECMP has some performance issue. I would say the first issue is the hash collision. Okay, so here's the example. In this network, like, we have 3 flows. Okay, 3 flows come from 3 hosts, from 3 different racks to 3 different hosts under the same rack. Okay, so the first flow, okay, it's good. It can achieve LAN rate. The second flow is also good, also line rate. Now I have the third flow, but unfortunately the third flow collides with the second flow, so they can only get half of the line rate. Okay, so this is a hash collision problem of the ECMP, and this problem is particularly very obvious when you have low entropy traffic. So in this example, right, the network bandwidth is degraded. The total aggregate network bandwidth is degraded by 1/3. It sounds okay, right? Just 1/3. But remember, in the AI, right, your job completion time depends on your slowest flows. So that means your job completion time will be double. So it's a big performance degradation. The second issue of the ECMP is that it does not really have the global congestion or bandwidth information. So this makes ECMP particularly very bad when there are some link failures in the network. So here's a rare example. So there are 4 switch, 2 leaf switch, 2 span switch, and we have 2 link between each switch pair. Okay. So when there's no link failures, okay, everything's good. Okay. So from the L0 to the L1, right, there are 2 next hop, and they have the same weight. Now, let's say one link between S1 to L1 is down, right? That means the S1 to L1, the bandwidth is reduced by half, but unfortunately, the ECMP cannot really track this. So it's still seeing that, okay, the S0 and S1, they have the same weight. And in this case, the ECMP cannot do a very good job. So given this limitation, right, how should ideal load balancing look like for the AI workload? So the first property should be fine granularity. That means we should be able to perform load balancing at packet or flow-like granularities. For example, for these green flows, we can split packets across all the available paths and aggregate the data at the receiver, probably using the NIC to do some reorder. Similarly, we can perform splitting to the green flows and to this blue flows. Okay, in this way, by using the packet splitting, right, we can ensure that all the flows they can achieve line rate, and we can achieve theoretical optimal performance in the network. So when there are link failures, right, our solution should be resilient, and this requires the knowledge of global congestion awareness. So in this example, right, since the S1 to L1, one of the link between S1 to L1 is down. So the load balancing should be able to adjust the weight. For example, here, we need to reduce the weight to the S1 from 10 to the 5. So well, in this way, right, we can achieve very good load balancing, even when there are some link failures. However, the ideal solution described in this slides, it may still require the NIC to do some work, because the NIC may receive out of order packets when we use a packet-based load balancing. So, but we can take one step further, right? We can leverage the switch to do both load balancing and reordering work, and this is called switch schedule fabric. The switch schedule fabric is completely transparent to end host, so we don't need support of the NIC or end host. So after talking about load balancing, optimization in the AI, let's take a look at the network virtualization in the AI cloud. So in traditional cloud, right, we have the multi-tenant VM running on the same host. So we typically have a virtual switch running on the host, either in hypervisor or in the DPU, right? We do the encapsulation, decapsulation. But in the AI, right, it's a different story, because the customer typically runs dedicated servers, so there's no contention in the end host. So in this case, when the multi-tenancy is a requirement, the top of rack switch can serve is a good choice to serve as a network's virtualization edge. For example, here, right, we can create 4 VSLAN tunnel endpoint, and we can use the BGP EVPN to create 2 VSLAN tunnel for 2 tenants, the red and the blue. So here are some of the thoughts on what we can do in the era of AI networking, and I believe there are a lot of interesting opportunities ahead. Yeah.
Thanks, Wei. So as you can see that we have talked about when AI comes, right, for the dominating of the application and evolution, we have taken a look at the involvement in one single unit, connect a few units within a short distance, right? Connect the unit point to point. RDMA is needed. But when we connect them, a large pool over distance, right, as a network to transmit to each other, right? Enhancement of how to route, right? How to enable multi-tenancy to share the resource. All these areas all have innovations and have work to do. So there's no one set solutions. I think this is why it's a very interesting time for us, which has networking, domain knowledges, has the experience, and also looking forward, right, to be very active in this world, to participate in building the next generation of network. Here is a group in SONiC that meeting happens every Thursday morning. It's free, right? That people who has interest here come to join to discuss the challenges, propose solutions, and form opinions and form solutions for the next generation. That the information, how to be there, join and be part of it is here. Everything is free. Join the group, join the meeting. Everyone is welcome here. Hopefully that it provides a forum, a platform for people who has the same interest, right, in the same area, in the networking, who come to share ideas and share innovations. With that, that concludes our presentation today. Go ahead.
I have a question for you. One of the slide problem of ECMP. You said caching collision is particularly bad for low entropy traffic.
Yep.
Are you implying the low entropy traffic more often time get collided?
Yes. So I want to give an example here. Let's say you have 3 paths, you only have 3 flows, right? It's very difficult for you to get good luck to attach one flow to a given path, right? But if you have 3,000 flow, it's a different story, right? You can achieve, more balancing, result. So this is what I mean by low entropy for ECMP.
Yeah, low entropy. I understand.
Yeah.
When let's say in a better network, right? They barely got collided. But here, are you inferring to say, in your experience, of your observation, you see the low entropy traffic are the major cause of the long tail?
I would say the low entropy traffic tend to have more serious problem or performance degradation when we use ECMP.
I see. That's truly what you mean.
Yeah.
Okay, got it. I have some idea here.
Yeah. So increase entropy, right?
That's what you mean.
Yeah.
Thank you.
Yeah.
Any other questions or thoughts to share? Okay, then with that, thanks everyone again.
Yeah.
Yeah.
Thank you.